The stage is yours.
Thank you very much. 1, 2, 3. All right. Hey, welcome, guys. Thanks for having us. It's amazing to see so many of you here. Is it OK with the mic? Everyone OK? Cool. So today we want to talk about reactive programming and how we manage to survive 1 billion requests per hour, basically, without paying like the world for it. So, but first, let me introduce us. Alex is one of our senior developers, and I'm the product owner of Mobfox and also running the business in Vienna. What we're doing is actually we're doing real-time auctioning. So it's called programmatic mobile advertising. It's the space we're in, and which is actually the whole reason why we have so much traffic, because we get all the traffic from the apps in the store. So if, for example, if we work with like Angry Birds or something like that, all their traffic will go to us as well, and from other apps as well. And we're going to have to find the best fitting ad in 300 milliseconds to serve to the user. So basically, we're doing that in 300 milliseconds, and we have to make many, many decisions. And Mobfox as a platform is called an exchange because we're in the middle between the publisher, the guys that have the apps, and the advertisers that have the ads, and they pay the money. So we're doing that so often that we came up to, we reached 1 billion requests per hour. Like, this is like a major, major thing for us. And we survived this thing actually by using great technology, and of course also by having these great people working with us. They come up with a good solution. So, you know, getting 1 billion requests and really making money out of them is not the simplest task. So, what we believe in, and which is also what brought us where we are now, is we believe in automation. Okay, I mean, you're developers. You know, I guess your heart is also beating for automation. You want to, every time you have like a task the second time, you want to already automate it, right? So this is the same thing we're doing. But the cool thing is that in our system and in the business we're in, there are so many things you can automate that it's actually getting very, very interesting to do that. Because, for example, we use some algorithms that we're able to grow us in revenue 3 times just because we are able to calculate prices more smart, and because we're able to decide who we send requests to and who we don't send requests to, because we know they will not make money at all. So this is great, and it's also stabilized the system. So you can imagine we love algorithms. Bring them on. If they make us more money, we'll be happy. So let me quickly introduce you to how Mobfox came to be. Not sure if you know Mobfox, because it's after the exit, it was a bit silent, because we were working on stabilizing our system. And let me tell you why. So the whole company, as a startup, was founded by this guy. I'm not sure if he's in the room. Okay, if he's in the room, come here. Because he's not working with us anymore. After he sold the company, he went to do another great adventure. So he founded in 2011, and it was a pretty big roller coaster, actually. So he was a one-man show. There was no version control whatsoever on the system, but he had already 800 servers, right? He was the only developer, which is why you don't need version control. But it's very bad, really, because we became a team and it didn't really work out. So we had PHP running the whole business, but we reached the limit. So we had PHP for asynchronous processing, but we have these 300 milliseconds. So keeping those milliseconds, like respecting this timeout, was super hard with this stack. It was really, really bad code, no indentation, no exception handling, and no system monitoring. I don't know how this guy made money, but whatever. So then we came in, some of us came in to help him out, okay? And the funny thing was that the code was very bad and everything, but he made money with it, okay? So it was you couldn't say that by looking at the code, you couldn't say if he was successful or not, but he was, right? So he had a huge publisher base, a lot of apps, a lot of traffic. He had the demand side, which is the advertisers. So that was great. He made millions in revenue per month. He had offices in London, Paris, and Vienna, and he had a huge potential. So what happened actually was that he found somebody to exit his company to, okay? And then this is when I came in, actually. So a company called Matomi bought Mobfox, and this happened while I was in Cuba. And if you visited Cuba, you know there is no internet, right? So I got an SMS that they sold Mobfox. Okay, so I like what? So how? What is happening, right? Where is it going? What's going on? But the only thing I did know was going to happen is that this guy is now like a rich guy. Okay, so he sold it for about 19 million, and then he went on to do his next venture, which is why now I am responsible for this thing. And it's so he kind of I inherited many challenges with the code base that I was just talking about, because it was in this kind of technology that you usually use for starting your business, but then again, you reach some limit, and then you think about rewriting the whole thing to survive. So what we had was about 250 million requests per hour in PHP. So how do you really process that so that you don't need to have like 2,000 servers and pay too much actually for it? How do you respect 300 milliseconds timeouts precisely without, when you do context switching, you come back after 500, it's too late. How do you handle 80K requests per server per second, which was back then what happened? How do you manage 800 servers without having any orchestration? And how do you ingest the data volume of 80,000 rows per second in a database? And how do you report on this stuff? So all of these questions, right? And many more. Like how do you manage multiple data centers and stuff without Docker? Everything. It was crazy. So also a challenge, because, as I said, it was only one guy, so you have to kind of find people to build a team, and where do you find these people that actually know about this technology on this kind of scale? So we solved those, okay? Everything is great. But by solving that with the technology Alex will tell you about, we brought in a bit of more challenges, right? So now we have 1 billion requests. Now we're respecting the timeouts because of Neti, by the way, it's technology we're using. We're handling 3 times more requests per server. We have Docker. Everything is on Docker today, so we can really easily manage the server base. And we're ingesting an incredible 200,000 rows per second into a Hadoop cluster. That blows my mind. So that's really cool, but I'm not the guy that developed this one. I'm just the guy that was able to find great people to work with us to make this happen, okay? So now I'm going to give the stage to Alex to explain to you reactive programming and how it helped us to manage all this load. Alex.
Thank you, Michael. Thank you. Yeah, OK. So we have these big numbers that Michael just presented. Of course, these numbers come with big challenges. And actually, let's see how we can solve these challenges. And the biggest challenge of all is actually finding an architecture that can should not stay in your way while solving all those challenges with minimum of compromise, right? So how to solve that, right? You can go the multi-threading servlet container way. That's one solution that you can have. And what is that? So you can have a client, a server, and a database. And once you have a request, everything works fine. You resolve some resource from the database in a blocking way, you still are able to deliver a response in a good time. So now, of course, you don't have only one client, you have multiple clients that are coming to your server in parallel. So you end up thinking of working in parallel with threads and do multi-threading. You would have a thread pool, and you would you will assign each request to a thread. So let's say we have a single core architecture. So now we have some threads that are fighting for CPU time and for resources on the database. So in a blocking way, so that takes time. And during that, you wait to resolve the resource. So if you have 100 concurrent clients, this solution works OK, still delivers. But what if you have a really high load? So like we have like 1 billion requests per hour. So what can you do? In this approach, you would end up having a big latency and you will not be able to deliver, you're spending the CPU time or in waiting time for resources to be resolved and in context switching between the threading. So you will end up with something like this. You would have requests queuing at the door without even being touched, right? So this is somewhere in China, by the way. So yeah, this cannot work, and what it brings is a huge latency, and actually, the latency doesn't grow in a linear way, but it spikes, and it's unpredictable. You cannot figure out how to scale this architecture. Of course, another way that I want to talk about is the reactive way of doing things. So what's different about the reactive way? The reactive way uses the event loop system. It's an event loop system and uses the reactor pattern. What it does, it's single-threaded, right? So we're thinking of only one thread that handles all kind of requests, of events. So you have an event can be anything. It can be a buffer that is ready to be read, or it's a file that has been loaded from the file system and it's ready to be consumed, or all the rows from the data from the database are being fetched and you can ingest them. So all of these events are going on an event loop. An event loop is basically a queue of events. You put these events on the queue and they are being processed whenever they occur. And this way, you limit the waiting time and you gain the full power of your hardware because you're working all the time. You have, at any moment, you have something to process. So, like I said, this brings your hardware to its full potential. You can deliver on a higher throughput. And what is great is that you have a predictable latency. So now the latency is growing, of course, if you have more and more requests, but it's growing in a linear way, and you know how to scale. What you do, you start multiple threads, and you can ingest that traffic. So to be more precise, we can do a comparison. So again, we're running on one core architecture. So on one core architecture, in the first way, you would have 3 threads that are handling 3 requests in parallel. Each one of them fights for the CPU. Once it gets the time from the CPU, it tries to resolve a resource from the database. It waits for it. It's a blocking call. You lose this, but it can deliver. At some point, you will have 3 responses out of it. You do a lot of context switching between the threads to be able to process them in parallel. So now, in the reactive way, what it does, you have only one thread that handles all 3 requests, and you can resolve the resource from the database in an asynchronous way. So when it is available, you ingest it. And you can deliver the 3 responses. So maybe you deliver the 3 responses in a longer time than one thread was delivering one response in the old way. But in total, you are much more faster than in the old architecture. So to understand it even better, this would be the event loop system. So nothing stops, right? There is no blocking call. Everything is asynchronous. It's so efficient, right? So you're using your full power, your hardware at its full power, right? So now everything that I said is cool, but we have to introduce some definitions here. So first of all, reactive programming. How can it be put in simple words? It means working with asynchronous streams of events in a threaded mindset, in a single-threaded mindset. So what can be a stream of events? Anything can be a stream of events. If you think of variables, configurations, data structures from the database, anything can be an event. and a stream of events. So what are we doing with this stream of events? We are listening to them and we are react accordingly. When we have an event, we process it and go on. Again, everything still is just theory, so I want to introduce some tools to apply this theory. So one of the tools that we are using at Mopbox is Eclipse Vertex. Well, what is Vertex? Vertex is a library that implements this event loop system on the JVM. So now it's not a web server, so it's not a server container, it's just a library. You can deploy it anywhere, however you want, start the service how many times you want. It doesn't constrain you in any way. The cool thing about it is that it has a lot of APIs for dealing with asynchronous file system, with HTTP server, even client, even has TCP and messaging, so low-level stuff, and it's polyglot. So it has implementations in many languages, Java, Scala, and many more. Plus, it has many modules that are already written in an asynchronous way. So, and those modules are packing blocking architectures like database connectors, and you can work with them in an asynchronous way. So if you have a MySQL database, you have this Vertex JDBC module that you can add to your project, and you work with MySQL in an asynchronous way. So that's cool, but let's see how actually Vertex is delivering on its promises. So now all the discussion was about a single core architecture, but as you may know, we don't have that anymore. We have multiple cores, so we would like to occupy all of them. Let's say we have an 8-core architecture. We can start 8 event loops, or verticals like they're called in Vertex. So now you have 8 threads practically, right? How do you not end up in the same architecture like the multi-threading one that I've just presented that cannot deliver? Well, the cool stuff about Vertex is that it has, as a core feature, it has an event bus. What does the event bus do is delivering asynchronous messages between all these threads. So whenever you have an event, whenever you want to share a state between the threads, you just send the message in an asynchronous way on the event bus, and at the other end, some controller will, the interested controller will consume that event. And you can go back and do whatever you have to do to process whatever you have to process. So this sounds great. I don't want to get in more details about Vertex Internals. You can find a lot of information on their website, but believe me, it's a great library. But because there is always a but, right? Vertex uses callbacks to respond to these events. And if there are any JavaScript developers here, are there? Yeah, so when you hear callbacks, you immediately think that about the callback hell. So a callback hell, for the ones that don't know about it, is calling a callback from inside the callback from inside the callback. So you'll have this going deeper and deeper, and that's just, it will end up duplicating code and to make the code unbearable. You would not understand what is going on there. So how can we solve that? And actually, the guys at Vertex solved it with the version 3.0, which can be Rxified, we can call it. So Vertex is Rxified from the version 3.0. What is Reactive Fix? So Reactive Fix is another tool, and actually it's a toolkit of functions to create, filter, and combine these event loops or these data streams. So to escape this callback hell. So like Vertex, Reactive Fix is a polyglot, so you can find implementations in different languages. At Mopfox, we're using the Java implementation, which is called RxJava. And now that's why Vertex has been Rxified. So now what you can do is to combine these event loops and avoid the callback hell. And our Reactive Fix and RxJava are using the observer pattern to bring a layer of abstractization on top of that. So what is the observer pattern? The observer has three main components, and actually has only three components. One is the observable, which packs a source, a source of events. Then you have some operators that you can chain them and you can transform your data however you want when it is being resolved. And you have a subscriber that just subscribes to this observable and gets all the events that are sent on the event loop and react accordingly to that, so it can process. It does the high processing part. You can end up on the transmission on an observable in two ways. You either have an error, so you can handle on error what is going to happen, or you can signal the completion of the transmission, which is a happy end. Those are, by the way, events. So now the juicy part, like I said, is combining these observables and to avoid the callback hell. So how can you do that? RxJava gives you an API to work with observables, and you can combine them in any way you want. I just exemplified here the zip function. It doesn't have anything to do with the compression. It just takes the first element from the first observable, the first element from the second one, combines them, and puts it on the event loop again. So it creates another observable of a different event resulted from the combination. And it does the same thing with the ones that follow in an asynchronous way. So now everything, these are the tools that we can use to solve our problem and to ingest as much traffic as we can. And to show you how exactly we're using those tools, I will show you quickly the request lifecycle that we have at Mopfox. So of course, somewhere there is a mobile device that needs an ad. It doesn't need an ad, but it has a space and it has to be filled in, and somebody wants to deliver an ad, to put an ad there. So it makes a request to our API that ends up in Vertex. So Vertex, what it does, it has a HTTP server boot up, and the HTTP server round robins requests to to a number of verticals that are being started. The number is not important. Vertex recommends to start the number of event loops that you start to be the maximum, double of your virtual cores. So it round robins the request, and at some point you end up processing a request. You have a lot of information from the request itself. You have the IP address. You have data about the user agent from the mobile device, but you still want to enhance that request with proprietary data and with third-party data, like resolving geo-IP location and resolving the user agent, so figuring out what operating system it has, and so on and so on. So you want to collect all this data, which for us it's external resources. So you want to resolve them in an asynchronous way and to combine all of them into a request context. So that's what we're doing with RxJava. So every resource for us is an observable, and we combine these observables till we get to one single observable that packs the request context. What we do with this, based on this request context, we can run an auction. So an auction is actually giving our partners the opportunity to bid on the ad space, to send an ad to fill that ad space. So we have a lot of requests to make outgoing requests to the outside world, and we want to do those in parallel. Here we're using a microservice. Vertex is also good at implementing microservices, but we have a microservice to do that in parallel, so to give each partner the maximum timeout available for him to respond. Once we have the responses, we collect them again into an observable. We are doing the reverse of the combination of observable, which is the flat map. So we are exploding one element in many others that are actually each one response from our partners. So now we have an observable of responses. We filter those, we validate those, and somehow we end up with a winner. So we deliver this to our publisher, and now, of course, our request ended, but we haven't made any money out of it because we don't know if the ad was actually shown to the final user. So at some point in time, another type of request comes in, which is an impression or a click, and we have to ingest this this request and bill our partners and make money out of it. So for that, we have to have a shared state, which is done through the event bus from Vertex. So we know which to associate the impression to actually a delivered ad. And now the request lifecycle really ends. What you have to consider is that you also want to log everything that happened into this. So I don't have much more time to show you all the other technologies that we're using at Mobfox. A couple of them, you can see them out there. The bottom part is mainly about reporting and ingesting all this volume of data. And now I will happily give back to Michael to do the closing part. So please, Michael, thank you. Thank you for doing. Yeah. You're okay.
Thanks, Alex. It sounds interesting. So for those of you who found this also interesting and you just quickly, right? I know we're out of time. For those of you who find this interesting and want to know more about it, you know, part of our future challenges is not only maintaining this thing and making it even better, but it's also using machine learning for making smart decisions instead of the statistical models we're doing now. Scheduling system for big data aggregation, writing UI and React and TypeScript, React.js. Using Grafana and Graphite for real-time system monitoring, really interesting one. And okay, launching our domain API to the public. So this is something that, you know, we're constantly having these huge challenges that you usually have, you know, usually talk about, I don't know, in the US or in the Silicon Valley. Somehow we manage to have these challenges here as well. So if you're interested in talking about these topics after this talk, please join us at 4:30 p.m. where the food is. Where the food is. It's in the mixed reality zone. We're going to be at some desk there that is free. We have these T-shirts, and thank you very much. And one more thing, can you turn around? So we're searching for smart people. If you find this interesting, please come and talk to us, okay? And photo. Great, thank you guys.
You stay a minute, come on. There are questions. We have questions today.
You have questions?
Yeah, there's one, somebody was wondering why you have chosen Java and not Scala. Any reasons to not choose Scala?
Yeah, can I? Yeah, of course. It's very hard to find developers for Scala, so that's why we picked Java. That's our main concern. There are a lot of Java developers that can be brought to this new kind of architecture, to reactive programming. And yeah, at some point maybe we go with Scala or with Clojure for some of you that know that technology. So yeah, but that's a separate concern. Now we're trying to scale also in the matter of the team. So we are looking. It's easier to look for Java developers.
Sounds great. Thank you for that great report on progress you have made in the last 9 months. Thank you, Michael.
Thank you, man.
Thank you, Alexandru.